Hello and welcome to this video lesson. In this video, we will be looking to see how we can use the second law of motion to solve real-life problems. Similar to kinematics and the steps that we've taken for those type of questions, we're going to follow the exact same procedures. So we're going to solve problems that are given to us using a 5-step process, starting with a pictorial representation or system diagram, moving into the physics representation, going into word representation, then mathematical representation, and finally the evaluation. In our first question, we get an elevator, and this elevator and its load have a combined mass of 1,600 kilogram and experience a force of gravity of 15,680. So basically, we got this number basically by multiplying by mass times the gravitational acceleration. That was 15,680 newtons. It is initially moving downward at 12 meters per second. To find the tension in the supporting cable when the elevator is brought to rest with a constant acceleration in a distance of 42 meters. Complete the solution process below. This is also a question that I've adapted from Mr. Chris Meyer from his notes from 2014. So let's draw this situation out. So we're going to sketch the situation, and we get an elevator. I'm going to draw it using a box. It's attached to a rope, and that's what's causing the tension force. And it's going to be in two different events or situation. We're going to have event 1 at the top one, and event 2 the bottom one. And the reason for that is because it's just moving downwards. We know that based on the question, velocity at stage 1 is equal to 12 meters per second, and velocity at stage 2 is 0 because it comes to a stop. We know that it has a constant acceleration. I'm going to assume that the acceleration is going down, but we will see if that's the case or not. There's going to be a certain distance which has been traveled, so I'm going to label that like this. This is going to be, or the displacement, sorry, from 1 to 2, so I'll write that here. And this is going to take a certain amount of time, which we don't know. I'm going to take down to be positive, and I'm going to use units of meters second, and this time kilograms for mass. This is 42 meters, and the mass is also given to us, so I'll just write the mass as well. This is 1,600 kilograms. Okay, I have all the information that I can have from the question. So basically, this is very similar to steps we've been taking previously, drawing a system diagram and putting all the information that we have from the question. In a physics representation, we're going to do the same thing. We're going to draw the position time, velocity time, acceleration time. So this is position, velocity, and acceleration. And in addition to that, we're going to draw the force diagram. You can also do the interaction diagram if you want, but I'm just going to do the force here. So in terms of our velocity, let's start with velocity. We start at 12 meters per second. Directions are in the same direction, so it's positive. And we end up at position 2 with a velocity of 0. So connect these. This is 1, this is 2. In terms of position, at starting position, we're here, and later on, we're below our initial position. Since down is positive, that means everything in this direction is positive. So I'm going to put a point right at stage 2. This is 1, and this is 2. And our slope starts pretty steep, and it ends up at a 0 value. So start steep, 0. So I connect these like this. Beautiful. And for our acceleration, that's the slope of this line over here, and the slope of this line is a negative. So that means that this is going in this direction. And we don't know what that value is. It's actually not 9.81 anymore. You can see that it's negative, meaning that since I assume that this is positive, the acceleration is actually in the opposite direction. The acceleration is actually going up here. The reason for it is we got an object that's just traveling in this direction and slowing down. And if it slows down, the direction of acceleration and velocity need to be in opposite directions. Now, for the force diagram, looking at our object during the time that it travels, we basically have it interacting with Earth. So with Earth, it will pull it downwards, and that's going to be the gravitational force. And it's not interacting anything on these sides. There's also an interaction here with the rope, which will be pulling it upwards. Since we know that it's going to get slowed down, we now have to start drawing the force diagram properly with proper magnitudes. This force over here needs to be bigger, so the actual acceleration at the end is going to be upwards, and because of that, I'm going to draw this force here a little bit bigger, and we're going to call this force of tension. And this is basically acting on the elevator from some sort of wall. So I'm not going to write it down in this case, but we know that it's acting from a wall somewhere or a motor, and it's acting on our elevator. And there's no other interactions, and therefore there is no other forces acting on this. So now that we have this, we can go ahead and solve the situation. We have assumed that acceleration is going down, so I'm going to put that in here, and let's go for it. For word representation, so describe the motion with no numbers and explain why, and any assumptions. So I'll just explain the motion really quickly. It starts at position 0, it moves in the downward direction. Its velocity starts at a high speed and it slows down to 0 at the very end, and its acceleration is constant throughout. So we are making an assumption though that acceleration is constant. We are also making an assumption that there is negligible air resistance here because there's no force, no other forces acting on it, so there's nothing that's actually pulling it upwards. And we don't have to deal with frictionless or anything in this case. So those are the main two assumptions here. So these are our assumptions. A few other things actually before we move on here in terms of the motion. The object is going downwards. Since it's going downwards, it needs, in order to slow down, it needs an acceleration that's moving in the opposite direction. So the acceleration needs to be going up. In order for acceleration to be up, that means there needs to be an unbalanced set of forces. And the unbalanced set of forces needs to be larger in the up direction. In order for the acceleration to be in that direction. Note that I've also assumed that the acceleration is actually going down. That's okay, because if we have to use the acceleration value, we'll just make sure that we're plugging in the proper value when we are doing our calculations. Our next step is the mathematical representation. So I'm just going to zoom out and do it on the side here just because we have a little bit more space here. And we have all the information to our left. In order to find a tension force, we can take either up or down to be positive. We're taking down to be positive here. We could use a different system of up and down, or sign convention we're using of force diagrams, but I'm just going to be consistent and use down to be positive. So in our case, the net force acting on our object, I'm going to take down to be positive, is going to equal to the force of the gravitational force plus the tension force. Now, this is also going to equal to the mass of the object multiplied by its acceleration. So we know that net force is equal to sum of forces, and it also equals to the mass times acceleration. I'm taking down to be positive here, so Fg, this one over here, is going to take the positive value because they're going in the same direction. And we know that Fg is 15680 plus the force of tension. I don't know what that value is, so I'm just going to leave it as this. It's equal to the mass. I know the mass is 1600, and I don't know the acceleration. In order to find this force of tension, I need to figure out the acceleration first and plug in that value. I can't find the acceleration based on the forces, but I can use this set of information to find the acceleration because I have the initial velocity, final velocity, and the displacement. So let's use that set of information down here to find the acceleration, and then we're going to plug it back in and solve for a tension force. Okay, the information that I have is velocity, displacement, and velocity 2 and acceleration, and the equation that I can use for this is velocity final is equal to initial velocity squared, final velocity squared is equal to initial velocity squared plus 2 times the acceleration times the displacement. I'm going to plug in all the values. Velocity 2 is 0. And 0 squared is just 0. Velocity 1 is 12 plus 2 times, and I'm taking down to be positive. These two are consistent, so I'm going to use a positive value. The acceleration is what I'm trying to find, so I'm just going to put A. And the displacement is also going down, and my positive is down, so I'm going to use a positive value here. I'm going to rearrange for A, and that's going to be 12 squared, which is 144, divided by 2, divided by 42. And I'm going to rearrange, actually this becomes negative, so my acceleration becomes 1.714 dot 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 negative. And it would make sense that it's negative because I'm assuming that it's going down, but it's actually going in the upward direction. Now I can plug that into here. So I have 15680 plus the force of tension is equal to 1600 times the acceleration. I'm taking down to be positive, and in terms of down, I know that the acceleration is going up, so I'm going to use a negative value. So that's negative 1.714. And then I'm going to plug everything in. So I'm going to get Ft is equal to, I'm going to have 1600 times the acceleration value that I just found, and that's negative 2742.8 minus, because I'm moving this into the other direction, and that's 15680. And when I put everything into my calculator, I will get 18422 dot 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 and a negative value. Okay, so then that would mean that Ft, or the tension force, is going to equal to approximately, I'm going to look at my values here, the least amount of significant figures is 2, so I'm going to round this to negative 18000 Newton, and basically I've been using down as my positive this whole time. So this is going to be the answer, or you can write it as 1800 Newton in the upward direction. And this is my final answer. And in terms of evaluation, does it actually make sense? Well, we can think about it in terms of direction. And in terms of direction, the tension force should be acting upwards in order to pull it, and it does, and that makes sense. The tension force is larger than the gravitational force. This is 1800, this is 15,000. Sorry, this is 18,000, this is 15,680, so this is bigger. That makes sense as well. And in terms of evaluation, there could always be questions on what would happen if there was air resistance. And if there was air resistance, that would mean there would be an extra set of force that's pushing it upwards, and that would affect the total acceleration. And if it took the same amount of distance for this to slow down, that would mean that there's an extra air resistance that also helped it. So that means that tension force wasn't as high of a value. So different ways that you can actually think about this, but make sure that when you are answering your questions, you write any assumptions that you had in order for me that whenever, or me or an examiner that's looking at your work to understand exactly what you're saying. Let's look at another question. So in the sample question, we got a road test and we got a driver that brakes. And the car's mass is 1,420. And the vehicle is moving at 64.8 kilometers per hour in the east direction. I'm going to turn that right into meters per second right away. This is going to be 18.0 meters per second exactly. And it comes to a stop after moving 729 meters in the east direction. And we wanted to determine the acceleration and force of friction and the time it took for it to stop. Okay, first step is to draw out the situation, and we will do that. We got a car. It is initially going at a speed of 18 meters per second. I'll write all the significant figures, and then at the end, it comes to a stop after braking. It will travel a distance of 729 meters, and we don't know how long this takes, and we don't know the acceleration. We know it's going to accelerate in this direction because it's slowing down, but I'm just going to leave it as that direction for now. And we are taking, most of the stuff is going to the right, including our displacement. So I'm going to take this side to be my positive. I'm going to use units of meters, seconds, and kilograms. And I will also include the mass here. Mass is also given to me as 1420. I think that's all the information that I have, and I have a nice system diagram which includes everything. I am going to start including my velocity, position, velocity, and acceleration time graphs. I'm taking right to be positive, so my starting speed is positive, reaches a 0 at the end. That's 1 and 2. Start at a high velocity, reaches a 0, so its slope reaches 0 at the end. That's 1, 2. And my acceleration is negative throughout this situation, and that makes sense because I have to be accelerating in the opposite direction to my motion if I want to slow down, and that is the case. For my force diagram, I am going to, it's going to be very important. I'm just going to draw it here. This is force diagram of the car. I'm going to compress all of its mass into this little point here. And what are the forces acting on it? Well, the driver is only pressing the brake, and when a brake is hit, the discs on the brake are going to kind of get into contact, and as they do, there's going to be a force of friction, and that force of friction is going to slow down the car. So in terms of my force diagram, one thing that I want you guys to notice in this question is that acceleration is to the right, and we don't really need to include the information up and down for our force diagram in this case, but we will anyways. There's a normal force from the ground on the car. There's going to be a force, a gravitational force. There's going to be some frictional force also from ground to the car. And most of the frictional force is coming from the brake, and that's the one that's most significant, and that's the one I'm going to draw. So this is the force of friction, and that's caused from the brakes. I'm not going to write exactly where the forces are coming from, but I will keep it in mind. When we do get into situations where we are doing third law of motion, then it becomes much more important to write where some of these forces are coming from. But for now, just know where they're coming from, and that's the most important thing. Okay, in terms of assumptions, we are definitely assuming that there is no or negligible air resistance. I'm just going to call it AR. And there is going to be constant acceleration, and that's not always the case. And then, well, we're going to assume that in our course it will be the case, but it's definitely not the case when the car is braking. Okay, determine the acceleration. So first we need to find the acceleration. To find the acceleration, we don't need to use the force diagram or anything on the forces. We purely have to use the information here because we already have initial velocity, final velocity, and displacement. So the equation we are going to use for part A is final velocity is going to equal to the initial velocity plus 2 times the acceleration times the displacement. Final velocity is 0 because it stops. Initial velocity is 18. It's going in this direction. My positive is in this direction, so I'm going to use positive 18 plus 2. The acceleration is what I'm trying to find, so that's just going to be acceleration. And my displacement is going to the right, and my positive is to the right, so this is going to be 729. So I'm going to move, I'm going to do A is equal to negative 18 squared divided by 2 divided by 729, and I will get negative 0.2 repeated for my answer here. And that would make sense because acceleration has to be in the opposite direction as to what I assumed in order for the object to slow down. I actually need to find the value, and my least number of significant figures in this question is 3, so my A, acceleration, would be approximately negative 0.222 meters per second squared in the right direction. I have my acceleration. I have to find my force of friction and the time to stop. So I can do time of stop actually pretty quickly because I can still use this set of information and use kinematics only. I don't really need to use forces, but let's just use the force diagram to do part B first. I'm going to move up a little bit, and let's do part B here. So in terms of my net force, F net, it's going to equal, and I'm doing only the x direction here because we got x and we got y. And I'm going to focus in the x direction because that's the way it's accelerating, and that's where the force of friction is in this direction. The only force that's acting in this direction is force of friction, and this is also going to be equal to the mass of our object multiplied by its acceleration. So we usually write the net force, what it equals to. It's always equals to two things. One is the sum of the forces, so I'll write that first, and it also equals to the mass times the acceleration. This is the mass of my system, which is just the car, multiplied by its acceleration in the x direction. Okay, now that I have this, I'm trying to find force of friction. So force of friction is going to equal to, once I write it like this, I no longer need this term. I only care about these two. And my mass in the question is 1420, and my acceleration I've already found. It's negative 0.2 repeated. And when I multiply the two values, I get that force of friction is equal to negative 315.5 repeated, and to three significant figures, my force of friction will equal to negative 316 newtons, and that's in the right direction. I'm still taking right to be my positive, and does this make sense? Well, it says it's negative 316 to the right direction. That means it's actually pointing in the left direction, and it is. So that's fantastic. And the magnitude of force of friction is just 360. Okay, let's highlight my answers. This one and this one. And finally, the last part of the question asks for the time it takes for it to stop. So do part C over here. In order to do that, I'm going to use the initial information. I have initial velocity, final velocity, and displacement, so I can just go ahead and find time using one of my 5 equations of motion. The equation that I need is displacement is equal to the initial velocity. For me, that's 1 plus the final velocity, that's velocity 2 divided by 2 multiplied by the time. I am going to rearrange for delta t, and that's going to equal to 2 multiplied by the displacement over velocity 1 plus velocity 2, and that's 2 times 729. Again, right is positive, so that's also positive, this is also positive, and this is 0. So we get divided by velocity 1, which is 18, plus 0. And when we do this, we end up getting that the change in time is 81 seconds. And I'm going to highlight this. Is this good in terms of our answers? Well, let's look. I think the best way to evaluate this is actually right based on the time it takes for it to stop, but you can actually also look at the question and see somebody's moving at 18 meters per second, which is approximately 64 kilometers per hour, and they press the brake, and it takes 729 meters for them to stop. I'm sorry, I guess in this question we did mention east to be our direction, so I'm going to have to go back and change these to east for my final answer. Sorry, going back to this, if somebody's going at 62 kilometers per hour and it takes them 729 meters to stop, this is almost a kilometer. That's not a good thing. Also, when you think about it, if it takes 81 seconds for the car to stop, that means that there's definitely something wrong with the brakes, and they need to figure out what the issue is as soon as possible. So this is not very realistic in terms of the solution. It's possible if somebody has terrible brakes for this to happen, but it is definitely dangerous brakes, and it does need to be fixed. In terms of acceleration, you can see the acceleration is a very small value, and even the force of friction is pretty small, and this usually the brakes have significantly higher force of friction acting on them. Also, if we had air resistance, things would change slightly. Assuming that the displacement, initial velocity, and final velocity wouldn't change, If we add air resistance, that means that we will have another force resisting the motion. And if that's the case, that would mean that the force of friction would actually be even smaller value or smaller magnitude than 316 Newton in this case. I hope that these two examples help you a little bit with practice on second law of motion. You gotta practice, practice, and practice with these types of questions. Please follow the 5-step solutions whenever you're doing them. And the more practice that you will do, the better you will get. And hopefully soon you will master these types of questions. Note that there is usually, once you have your system diagram, your motions, and your force diagram, you're good to go, and solving the problem now is going to be very different in different situations. Sometimes you have to start with force analysis, sometimes you have to use kinematics. If you're given enough information in the question, if you're given 3 sets of information in the kinematics, then you can always find the acceleration. The link between forces and kinematics is acceleration. So if you can find acceleration using kinematics, use that first and then use forces. If you can find acceleration using forces, find that and then solve the stuff in kinematics. So it all depends on what information you're given. You could be given a question where you only have 2 pieces of information and you will have to find the others. And in that case, you might be given more information about the forces, and you can use the forces to come up with the acceleration value. And then you will now have 3 sets of information and you can solve the other things. So once again, it's just with practice, you'll get better at this and you are going to master the skill. Very important to be able to use second law of motion in both grade 11 and 12. All right, folks, have a wonderful day.